Using the reference method, what is the maximum deflection of the beam below? Knowing the beam, use the steel beam W10 by 19, and the E and the I can be checked in the AISC reference. The hint is that the beam will bend around the x-axis, and so you can use the IX in your calculation. Before you start with this problem, let's discuss about what is an I-beam. So I have over here is a plastic I-beam one. You can see if we look on this side, it look like the I ladder, right? So we're gonna call that one is I-beam. The correct way to call that one is actually Y flange beam, but in industry sometimes they call that one is I-beam as well. For the I-beam over here, they're gonna have y-axis and x-axis. If the x-axis, it will bend around the I ladder over here. You see that if I keep that like the I ladder, it's very hard to bend. It's very hard to bend. However, if I rotate it over here, it's not I anymore. It's an X ladder. You see that like an X ladder, and if I bend that, it's very easy to bend. Okay. So if I bend that around the I ladder, it will be x-axis. If I bend that around the x ladder, it will be y-axis. And because we want to maximize the capacity of the material, we should bend that around the I-axis. That's why you see that people call I-beam, they don't call X-beam. Later on of this course, when we move to steel structure, we're going to discuss more about that. But for now, just keep in mind this is an I-beam. For this problem, the first thing you need to do is to check the reference. So what I'm going to do is that I will go to the home page, go to reference, go to shear moment deflection diagram, and I'm going to find the reference that is similar to the load diagram we have over here. We have one pin and one roller, and this one is uniform load. So I can check. So I see that figure 1 over here is very similar to the one we need to look for. And if I check for the deflection will denoted by the letter alpha, the delta over here. So you see the delta max is at the center, which means the deflection, the maximum deflection is at the center, with the value is 5 multiplied by WL to the power of 4 divided by 384 EI. So I'm gonna copy that. I'm gonna copy that formula here. So we have, and I'm gonna type this one by formula equation. So we have alpha max equal to 5 divided by 3A4, and we have 5WL to the power of 4 divided by 3A4 EI. Okay. So now we need to find W. So we already know that W will is equal to this value is 6 pound-foot, and then we have L will equal to 13 feet. So now we need to look for E over here, and because this one is steel, you see that the node over here, check E on the formula reference. So what I'm gonna do is that I go back here, go to formula, and I check for steel. For steel, the elastic modulus E is 29 multiplied by 10 to the power of 6 psi. So I'm gonna write it here. E will equal to 29 multiplied by 10 to the power of 6 psi. So now we have W, we have L, we have E. So now let's check for I. If you see on my note over here, you can see check I in the AISC reference. So if you go to Canvas here, AISC, AISC stands for American Institute of Steel Construction. We're gonna learn more deeply when we move to the steel beam design. However, for now, just click on that and I'm gonna show you how to find it. So now we need to check for the beam 10 by 19. So what I'm gonna do, I'm gonna check for W 10 by 19. You see 10 by 19 over here. And the way the AISC format over here is that they have a very big table. And the table over here is so big, so they will divide that into 2 pages. So you see, this one is actually continue to this page. So let me open that in 2 pages for you to get a better idea. So for example, this one, so you see that this one over here is actually a continue of the left one. Okay, so you see that 19 over here we match with the 19 over here. Okay, let me open that up a little bit bigger for you, easy to see. And let's open this one. All right, let's move it here. Okay, so now we have the I-axis. Let's check for the I-axis. This is the x-axis. You see that? And the I-axis is this column. If I go all the way down here, I can see that I-axis will equal to 96.3. And the unit over here is inch to the power of 4. Inch to the power of 4. So this one is 19. You see that? 19 matching over here. 19. This one will be 96.3. So what I'm gonna do here, tie it over here. So we have I will equal to 96.3 inch to the power of 4. Okay. And because we have here is inches, this one is inches as well, and this one is feet. So we need to convert this one to feet to matching with the other one. So let's put that one pound foot. Let's give a space here. All right, so now let's convert this one to pound over inches. So we're gonna have a 60 pound And because we have 1 foot, we equal to 12 inches. So now this one will equal to a 60 divided by 12. I'm gonna have that one is 71.6, which roughly around 72 pound inch. Okay, and this one we equal to 13 multiplied by 12, we equal to 156 inch. Okay, so for now I just replace I will plug in everything I have so far. So I just plug in equal to, and W I have that one is 72 and multiplied by L. L is 156.4 multiplied by E. E is 29 multiplied by 10 to the power of 6 multiplied by I. I will have that one in 96.3. And finally, I have the deflection over here will equal to around 0.19 something. So I will round up 0.2 inches. So the beam over here with this material, with this type of load, with the type of support showing over here, it will deflect around, let me put here, it will deflect around 0.2 inches. It will deflect around 0.2 inches.